Morning, students. Today we're going to discuss about a topic called colloidal dispersions. So colloidal dispersions are an important class of mixtures that lie between true solutions and suspensions. In a colloidal system, one substance is dispersed uniformly throughout another medium. But here the particles are larger than the molecules and smaller than those found in case of suspensions. So a colloidal dispersion consists mainly of two main components, dispersed phase and dispersion medium. So here dispersed phase means here the substance present as small particles, and dispersion medium means it's a continuous phase in which the particles are distributed. So the particle size in colloids typically ranges from the size range of colloidal particles mainly ranges from 1 nanometer to 1000 nanometers. Because of this intermediate size, colloids will show unique properties that distinguish them from both true solutions and post suspensions. So next, an example for a colloidal system is colloids are mainly found in our everyday life and pharmaceutical systems. And some examples for this colloidal systems include milk, that is a liquid in liquid emulsion. Then fog is liquid in gas type. Then smoke is an example for colloidal system. Then gels like a jelly. These are also milk, fog, smoke, gel, etc. All these are examples for colloidal systems. And in case of pharmacy, in the field of pharmacy, colloidal dispersions are mainly used in drug delivery systems like ointments and suspensions. Then, and also this colloidal dispersion will expect several distinctive properties like optical property, kinetic property, as well as electrical property. So in this topic, we are going to discuss about optical properties and kinetic properties. So optical property means it involves Tyndall effect, Brownian moment, then etc. Like that. Then and colloids, the classification of colloidal dispersion. Colloids can be classified based on the nature of dispersed phase as well as the dispersion medium, like solution, emulsion, foam, aerosol, etc. Then coming to the importance of this colloidal dispersions or colloidal systems. In case of pharmacy, it plays a very crucial role in pharmaceutical sciences. Like it will improve the drug solubility and the bioavailability. Then can be used in case of controlled drug delivery systems. Then important in the case of formulations like creams, gels, suspensions, etc. And in conclusion, in summary, we can say that colloidal dispersions are an important systems with unique physical as well as chemical properties. In their particle size, their intermediate particle size and stability will make them highly valuable in both our everyday applications and in advanced pharmaceutical formulations. So today's session we will going to discuss about the properties of colloids, optical properties, and mainly three properties are there: optical property, kinetic property, and electrical properties. So in this session we are going to discuss about optical properties and kinetic properties. So colloids show three major categories of properties, like optical properties, kinetic properties, and electrical properties. So in this section, we mainly focus on optical and kinetic properties. In these properties, optical and kinetic properties, will help us to understand about the particle size, their movement and behavior in the dispersion medium. So next is the optical properties of colloids. So optical properties of colloids will help us to determine the size of colloidal particles, shape, structure, and molecular weight. And the source of light and the solving power of an optical system or a microscope that will mainly determine the precision and usefulness of such information. And the main optical properties of colloids are: first one is the Tyndall effect, second one is the electron microscopy, and third one is the light scattering. So these three are the main optical properties of colloids. And these are useful analytical tools in pharmaceutical as well as in chemical sciences. First one is the Faraday Kinetic. So when a strong wave of light when it passes through a colloidal solution, the lights get scattered due to the presence of colloidal particles. And this scattering will produce a visible cone of light in the colloidal solution, and that cone is called Tyndall cone. And the formation of that Tyndall cone is known as Faraday-Tyndall effect. For example, milk in water. So milk in water shows the Tyndall effect because of the presence of colloidal particles. These colloidal particles will scatter the light. Due to the scattering of colloidal particles, the Tyndall effect is formed. And an important point is that the true solutions do not show this Tyndall effect because their particles are too small to scatter the light. Only the colloidal particles will show the Tyndall effect. True solutions do not show Tyndall effect because of their um, too small particle size. Small particles will not scatter the light. So in this figure, you can see that the solution, when light passes through a solution as well as a mixture of milk in water. So here you can see that the solution will not show any Tyndall effect due to the small size of particles in solution. But in case of milk in water, you can see a Tyndall cone due to the scattering of the colloidal particles. So true solution does not show any Tyndall effect due to the small particle size. But in case of milk in water suspension, it will show Tyndall effect due to the scattering of light due to the presence of colloidal particles or due to the presence of large particle size. So here, this Tyndall cone can be observed with the help of an ultra microscope. So ultra microscope will help us to observe the scattered light points in a colloidal solution. So let us see how it works. First, an intense light beam is passed through a colloidal solution and it is viewed against a dark background. And the bright scattered spots represent colloidal particles. And this scattering will allow counting and studying the particles indirectly. So what you see in this image is an example of Tyndall effect in nature. So the sun's light is passing through tiny particles just suspended in the air, such as dust particles, mist droplets, water vapors, smoke particles, etc. All these particles are present or suspended in the air. And these tiny suspended particles will scatter the light in different directions. And because of this scattering, the path of the light becomes visible or becomes bright beams or sunbeams. So next property is the electron microscope. The electron microscopy is used to determine the size, shape, and structure of chlorine particles. And why electron microscope? Because ordinary microscopes they use visible light with low resolving power. But electron microscopes they have high resolving power. Resolving power is this the ability to distinguish two nearby particles separately. And that is denoted in terms of small letter d, smallest distance between two particles. That is the resolving power. So electron microscopy have high resolving power, right? Normal optical microscope. But the resolving power mainly depends on the wavelength of light, that is lambda. So smaller the wavelength means higher resolution, or smaller will be the d. Distance between two particles will be small. So smaller wavelength means higher resolution. And when we compare optical microscope and electron microscope, resolution. Optical microscope resolution is about 20 nanometer, and electron microscope resolution is about 0.01 meter. And thus, electron microscopes can visualize extremely tiny colloidal particles. And visible light has a larger wavelength, and so less resolution. And electron beams have much smaller wavelengths, so they give clearer images than ordinary microscope. So this is the advantage of using electron microscope over optical microscope. Next optical property is the light scattering. Light scattering also helps to determine the molecular weight, size of particles, and shape of coronal particles. And this light scattering is described in terms of probability. When light passes through a colloidal solution, the particles will scatter a part of light, and this will decreases the intensity of light due to scattering. And this decrease in the intensity of light is called turbidity. That is represented as rho. And higher turbidity means more scattering. If the light scattering is more, means it will show higher turbidity. This equation is used in light scattering studies of colloids, mainly to determine or mainly to calculate the molecular weight of colloids, that is M. Molecular weight of colloid is denoted as capital M. And the equation is Hc by tau is equal to 1 by n plus 2 b. And each term represents capital H is the optical constant, C is the concentration of the colloid, then tau is the turbidity, that means the amount of light scattered. Then capital M is the molecular weight of colloidal particles, and capital B, that is the interaction constant. And the main principle behind this equation is this is a linear equation, that is this is a linear equation where Hc by tau, that is plotted in the y-axis, concentration is plotted in the x-axis, and the intercept on y-axis is 1 by m, and the slope gives 2t. And the graph interpretation, when you interpret the graph, we are plotting Hc by tau versus C. Hc by tau on y-axis and C on the x-axis. You get a straight line. And from the y-intercept you give 1 by m. So m is equal to 1 by intercept, and this gives the molecular weight of colloidal particle. And the slope is 2b. So b is equal to slope by 2, and this gives interaction constant, that is p. And this equation helps us to determine the molecular weight of colloids, that is capital N, and also the degree of interaction between the particles, that is the B, capital B. So these two terms will obtained from this graph. So next we will move on to the kinetic properties of colloids. So kinetic properties of colloids mean these are the properties related to the motion or the movement of particles, colloidal particles in exclusion medium. In a colloidal system, the particles are continuously moving in the medium because they are extremely small and are influenced by heat energy, gravity, and electrical forces. So kinetic properties will describe how colloidal particles behave while suspended in a medium such as liquid or gas. And these motions of particles are classified mainly into three groups. First one is the thermally induced motion, second one is gravitationally induced motion, and electrically induced. So in thermally induced motion, these are mainly occur due to heat energy, and it includes Brownian movement, diffusion, and osmosis. And gravitationally induced motion, that includes sedimentation and viscosity. Third one is the electrically induced motion that includes electrophoresis, electroosmosis, etc. So first, thermally induced. So in that, Brownian motion. Brownian motion means it is a zigzag, random zigzag movement of colloidal particles. Diffusion means movement of particles from higher concentration to lower concentration. Osmosis means movement of the solvent molecules through semi-permeable membrane. And the solvent will move from dilute solution to concentrated solution. Then gravitationally induced. First one is the sedimentation. That means the settle down of heavier colloidal particles due to gravitational force. And viscosity means it is the resistance offered by a colloidal solution to flow. That means higher viscosity means particles move free and less freely. Then electrically induced motion induced electrophoresis, electroosmosis. And let's see what Brownian motion. So Brownian motion means it is a continuous and zigzag movement of colloidal particles, which are suspended in a dispersion medium. And the particles never remain in a static condition. They keep moving regularly in all directions in the medium. And this Brownian motion happens mainly because the molecules of the dispersion medium will constantly move. And these fast-moving molecules will collide unevenly with colloidal particles. And since collisions occur from different directions, particles move randomly in zigzag movement or zigzag pattern. And this Brownian motion was discovered by a scientist, a Scottish botanist known as Robert Bell. And the main movement that is the zigzag motion of colloidal particles. And the zigzag motion means the particles will move irregularly and there will be no fixed direction for the movement of particles and they will constantly changing their movement path. For example, the movement of dust particles will dancing in sunlight. That is an example for this zigzag movement. And this colloidal particles, because of this colloidal particles are very tiny, this movement can be visualized only using electron microscope. Because ordinary microscope cannot clearly show their movement, and the electron microscope will help us to observe their irregular motion. So under electron microscope, particles will appear as tiny, bright moving specks. And again, factors affecting Brownian motion. Brownian movement increases when the particle size decreases. And Brownian moment decreases or even stops on increasing the viscosity of the dispersion medium. And then what are the importance of this Brownian motion? Why it is important? Because Brownian motion helps to prevent the settling of colloidal particles and it maintains stability of colloidal system. And it also keeps particles evenly distributed in the medium. So without Brownian motion, particles would settle down easily due to gravitational force. So in order to prevent settling, Brownian motion is important. And also to maintain the stability of the periodic system, this Brownian movement is important. And uh, let's see some examples of Brownian motion in daily use. It includes the milk particles moving in liquid, then smoke particles present in air, then dust particles present in space. All these are examples in our daily life for this Brownian motion. Diffusion. Diffusion means it is the movement of solute particles from an area of higher concentration to an area of lower concentration until the concentration becomes uniform throughout. So the underlying principle in diffusion is Fick's law. It states that particles will diffuse continuously while their concentration gradient and the equilibrium is reached. So let us see the diagram. You can see a box over here, and the box is divided into two halves. Left side shows high concentration, and the right hand side shows low concentration. So the left side shows many blue circles that represent solute particles packed closely together. And the right side means low concentration, fewer particles are present. And the red arrow shows the direction of particle movement from high concentration to lower concentration. And the result is over the time, particles will spread out evenly until equilibrium is achieved. So diffusion means it's a passive process. It doesn't require any kind of energy. So the rate of diffusion in colloidal system is expressed by Fick's first law. That is dq by dt is equal to minus ds into dc by dx. Here dq by dt is the rate of diffusion, amount of solute diffusing per unit. Capital D is the diffusion coefficient that depends on particle size, medium viscosity, temperature, etc. Then S is the surface area available for the diffusion. Then dC by dx is the concentration gradient, that is the change in concentration with distance. Then the negative sign, or the minus sign, indicates the diffusion occurs down the concentration gradient, that is from high to low concentration. And this equation tells us that the diffusion rate is proportional to both the concentration gradient as well as the surface area. And the second equation represents the diffusion coefficient for spherical colloidal particles. And the equation is D is equal to RT by 6 pi eta Rn cube root of 4 pi n by 3m V dash. And here R is the gas constant, T is the absolute temperature, eta is the viscosity of the medium, then small r is the radius of the colloidal particle, then capital N is the Avogadro's number, then capital M is the molecular weight of the dispersed phase, then V is the specific volume of the dispersed phase. And the first fraction, that is the RT by 6 pi eta Rn, that resembles the Stokes-Einstein relation, which shows that the diffusion is faster at a higher temperature and slower in more viscous medium or for larger particles. And the second term, that is the cube root term, represents the number density of particles in the colloidal system. That means particle size and molecular properties to diffusion behavior. So overall meaning of this equation is smaller particles will diffuse faster than larger particles. Then higher temperature will increases the diffusion rate. Then higher viscosity will slows down the diffusion rate. And from the above equation, we can assume 3 points. First point, the diffusion rate increases with decrease in particle size or the molecular weight. From the Stokes-Einstein relation, the smaller particles experience less resistance in the medium and they will diffuse faster. Similarly, lower molecular weight means lighter particles. They move more easily than heavier particles. In short, we can say that smaller and lighter particles will diffuse more rapidly. The second assumption we can make that is the diffusion will increases with increase in temperature. That means the temperature provides kinetic energy to the colloidal particles. So higher thermal energy means it will faster the random motion of the particles, and it will lead to higher diffusion rate. In short, we can say that heating a system will speed up the diffusion rate. Then the third assumption is that diffusion will decreases with increase in viscosity of the dispersion medium. That means viscosity is the thickness or the resistance of the medium to flow. So a more viscous medium will slows down the particle movement. For example, we can say that diffusion is slower in honey than that in case of water. So these are the three assumptions we can make from the above equations. So in short, we can say that fast diffusion will happens in case of small particles, low molecular weight, high temperature, and in low viscous conditions. Whereas slow diffusion will take part in large particles, high molecular weight, low temperature, as well as high viscous conditions. Next kinetic property is the osmotic pressure. So osmotic pressure means it is the pressure which is required to stop the flow of solvent molecules through a semi-permeable membrane that is separating two solutions of different concentrations. So it is the pressure required to stop the flow of solvent molecules through a semi-permeable membrane separating two solutions of different concentrations. It is a colligative property. That means it depends only on the number of solute particles in the dispersion medium, not on their nature or type. And in simpler terms, we can say that if more solute particles is there, it shows higher osmotic pressure. And it is described by Van Hoff equation, that is pi equal to CRT, where pi is the osmotic pressure, C is the concentration, molar concentration of solute, R is the gas constant, and T is the absolute temperature in Kelvin. So we can say that osmotic pressure increases with the concentration. That means if more solute particles are there, the osmotic pressure will be increased. And it increases with the temperature also. Osmotic temperature increases with temperature. Since higher thermal energy enhances the kinetic energy. And for dilute solutions, this equation allows calculation of the molecular weight of colloids or the macromolecules. That is m equal to CRT by pi. That is derived by rearranging this Van Hoff equation. We can written as m equal to CRT by pi. That is equation for calculating molecular weight of colloid, very dilute solutions. In case of concentrated colloidal dispersions, where the number of colloidal particles are high, we can write the equation, the above equation as pi by Cg is equal to RT into 1 by n plus Vcg. So here pi is the osmotic pressure, Cg is the concentration of colloidal particles, R is the gas constant, T is the absolute temperature, m is the molecular weight of colloid, and B is the interaction constant. So this equation modifies the simple Van Hoff relation, I equal to CRT. So this equation is mainly when the colloidal this equation is mainly used when the colloidal particles are high in concentrations. So we'll get a graph like this. So the graph plots pi by Cg on the y-axis and Cg on the x-axis. So it gives three lines, line 1, 2, and 3. So the line 1, that is for ideal system. That means it gives line 1 means it is a straight line with slope 0, and intercept is RT by M. And this represents an ideal solution that obeys the Rolle's law, that is no particle interaction, mainly for solutions. Then line 2 and line 3, these are real systems. So these are somewhat slanted lines with a positive slope. And the slope corresponds to B, that means the interaction constant. And different slopes indicate different strength of particle interactions. So here the y-intercept is RT by M. That means it gives the molecular weight of colloids, RT by M. M is the molecular weight. So this intercept, y-intercept will give the molecular weight of the colloid. So higher intercept means smaller molecular weight. That is RT by M is inversely proportional to molecular weight. So higher intercept means smaller molecular weight. Then the slope will give the B value. That indicates the extent of non-ideal behavior. So larger the slope means stronger the particle interaction. Then ideal versus real system, line 1 versus line 2 and 3. Line 1 means there is no interaction, diffusion and osmotic pressure, and that follows simple laws. Line 2 and 3 means deviations due to colloidal particle interaction or some electrostatic effects. Next kinetic property is the sedimentation. So sedimentation means it is the process where the particles in a dispersion settle down under the influence of gravitational force. But in case of single suspensions like sand in water, etc., the particles will settle easily because their gravity dominates. But in case of colloidal particles, their size is extremely small, is 1 nanometer to 0.5 micrometer. So at this size, Brownian motion counteracts the gravity. As a result, the colloidal particles do not settle under normal gravitational force. So we need to apply stronger force than gravity is needed. So in order to sediment the colloidal particles, we need to apply ultracentrifugation. So ultracentrifugation means it will apply very high centrifugal force and that will overcome the Brownian motion. And this allows the colloidal particles to settle based on the molecular. And the molecular weight M of colloidal particle can be determined by using a formula M is equal to RTS by D into 1 minus Vp0. Here R is the gas constant, C is the absolute temperature, S is the sedimentation constant, that is the rate of settling. Then D is the diffusion coefficient, V is the partial specific volume of particles, then rho 0 is the density of the dispersion medium. In this slide, the image shows that when Brownian motion increases, sedimentation decreases. That means when particles are very small in size, the random thermal motion, the Brownian motion keeps them suspended, and that resists the gravity. When sedimentation increases, the stability will decrease. That means larger particles or weaker Brownian motion allow sedimentation, and as particles settle, that makes the suspension loses stability. So when Brownian motion increases, sedimentation decreases. So in order to make the suspension in a stable condition, we need to provide Brownian motion. Then only the stability can be improved. So Brownian motion provides kinetic energy that keeps the colloidal particles dispersed. Gravity or sedimentation that pulls the particles downward, and the stability of suspension depends on which force dominates. That means if Brownian motion is stronger, the particles remain dispersed in the medium and it will make the system stable. If sedimentation is stronger, the particles will settle down at the bottom, and that leads to unstable system. And the sedimentation rate can also be calculated by using Stokes law. And this Stokes law shows larger particles, high density differences, low viscosity particles. This will increase sedimentation rate. Last kinetic property is viscosity. So viscosity means it is the resistance of a fluid to flow when stress is. That means if a more viscous liquid, like honey, requires greater force to make it flow compared to a less viscous liquid like water. So viscosity in colloidal system. In colloidal dispersions, the suspended particles affect the fluid's viscosity. That means the presence of particles increases the internal friction, making the fluid flow more slowly. The effect depends on particle size, shape, and concentration. And Einstein developed an equation for the flow of dilute colloidal dispersions of spherical particles. Eta is equal to eta 0 into 1 plus 2.5 psi, where eta is the viscosity of dispersion, eta 0 is the viscosity of the dispersion medium, phi is the volume fraction of viscosity particles. That means as the particle concentration, that is psi, increases, viscosity rises linearly. The factor 2.5 is specific to spherical particles in linear systems. And this equation is valid only for low concentrations where particles do not interact strongly.